Okay, so in the now we have discussing unit 2, that is the continuity, compactness and connectedness. So first we will like to give you a definition of continuity. So can somebody tell me, if I want to define a continuity, what should I define first? If I want to define a continuous function, then what should I define first? Or what is the requirement is there to define? Yes, anyone? To define a continuity, continuous function, we require a limit of a function. And what you have studied in your previous semester is a limit of a function over or a real valued function. Now here we are talking about the limit of a function in a metric space. So if you have a metric space, a function which is defined over metric space to another metric space, then when you can say a function has a limit L as x approaching to the point, to the fixed point A. Likewise, if you have a function from A to R, where A is a subset of R, that means you have a real valued function whose domain is a subset of a real number. If I want to say that this f function has a limit, that means if I want to say the limit of f of x is equal to L whenever x tends to A, then by definition, what we know it is for given epsilon greater than 0, there exists a delta greater than 0 such that distance between this, that means 0 less than mod x minus A less than delta, implies f of x minus L less than epsilon. So this was the definition of continuous function, sorry, limit of a function. If your function is a real valued function and whose domain is also a real number. Now, the next things that we need to discuss is a limit of a function in a metric space. So when we can say it's just slightly extension or generalization of this definition that we have here. So we'll generalize this definition for limit of a function where your function is defined over x, where x is a metric space, to a y, which is also a metric space. So for that, I'm just taking this two matrices, let's say x of d1 and y of d2 be a metric spaces, and let's say the point A is belongs to x, is a fixed point in x. Let f be a function from x to y. If I want to say that fx is said to have or is said to approach L whenever where this L is belongs to Y, whenever X approaches or approach to A, if for given epsilon greater than 0, there exists a delta greater than 0 such that d2 of fx minus L less than epsilon whenever 0 deleted neighborhood of A, that is 0 less than dx minus A less than delta. So here we have used the definition of a deleted neighborhood. That means whenever this x approaching to A, f of x is approaching to L. By notation, we are writing this as in the, we denote this is by limit of x tends to A, f of x is L, or I can say fx is tends to A as x tends to L, or sorry, A. So we should note here that if I consider your x is R and y is also R with usual metric, then we have, as per the definition previously, that is d2 of fx R, fx L is equal to mode of f of x minus L, and d1 of x comma A is nothing but the mode of x minus A. So that the above definition which we have discussed is reduced to the one given for real valued function. That means which we have defined over in the previous slide, that is for real valued function. That is this which we have here. So it is this definition is generalization of the things which we already discussed for real valued function. So we can say that this is the a limit of a function. It is there. Obviously, when we have a limit, we have certain things to discuss, that a limit of a function is always unique, that you can discuss, and that I'm giving you as a homework to discuss or to prove. Here we'll discuss some properties of limit of a function. Let us say this x comma d be a metric space, and let us consider some point A, it is in X. Let F and G be a real valued function whose domain are subset of domains are subset of x. It's real valued function. So I'm taking the function which is from A to R, where A is a subset of X. And similarly, G is also from A to R, where A is a subset of X. And I'm considering this real valued function. That means the range, it is in R with usual matrix. So also I require that quantity. So the range is in R with usual matrix. Then, and also I required the function, this is limit of f of x is L as x tends to A, and the limit of g of x is L as x tends to A. Not L, but let's say M. So now where this L and M, both of them are belongs to R, then we can prove the following. The first one is limit of sum is the sum of limit. That means limit of fx plus gx as is equal to L plus M as x tends to A. Second, a limit of fx minus gx is L minus M as x tends to A. The third one, a limit of x tends to limit of fx into gx is equal to L into M as x tends to A. And the fourth one is limit of fx upon g of x is equal to L by M if M is not equal to 0 as x tends to A. So the question is why I have taken here a domain as a subset of R. Sorry, codomain is a real number. That means the range is a real number. Why I have taken that? Because this L and M are in R, and if you want that these two quantities should having the addition, that means if I define your function from x to y, let's say, and then this images what we have as image of whatever the image it is in L or M, they are in y, and we don't know whether which type of operation, addition operation in y is there. So that is fx. Also we have fx plus fy. So this also cannot be defined. It is in the range. So for that, I am defining this is as a real number, as a range. It can be, if you want to extend this result, then you require this your y should be a vector space. If you define a y as a vector space, then you are able to discuss all the things in general for matrix space to another matrix space. But we are not dealing with that situation. We'll consider, or whenever we are talking about this continuous function, most of the time we'll restrict ourselves for real valued function. over on the metric space or define over the metric space. So here I want to prove that first quantity. If I prove the first one, second one I'm giving you as a homework, and the third and fourth also we can discuss here. In fact, third is also I'm giving you as a homework. So no, third I will do it, no problem. And the fourth also we can do it here. So this is I'm giving you as a homework that you can do it yourself. Let us try to prove now the first statement. So what is given is this quantity and this quantity is true. So by definition, we can say that given that limit of f of x is L as x tends to a, so we can say that for given epsilon greater than 0, there exists some delta 1 greater than 0 such that mode of f of x minus L, because fx it is in R, L is also in R with usual matrix. That's why I can take mode here less than epsilon whenever d1 of xa is less than delta 1. So D is a metric on X. Also given that limit of g of x is m as x tends to a. So therefore, there exists some delta 2 greater than 0 such that mode of g of x minus m is less than epsilon whenever d1 of x minus a is less than delta 2. What is our objective is to prove that mode of f of x plus g of x minus L plus m is less than epsilon whenever some x minus a or d1 of x comma a is less than some delta. So I'll calculate what should be the delta is. So I'll consider take the delta equal to minimum of delta 1 and delta 2. So if I take this as a delta 1 and delta 2, then if your d of x minus a is less than delta, then both this situation, that is d1 of x a is less than delta 1 is true due to this delta is the minimum of this two. So then you can say that d1 x comma a is less than delta 1 and d1 of x comma a is less than delta. Both these things is true. So now consider, I will start with mode of fx plus gx minus L plus m. So by triangle inequality and rearranging these terms, we can say that this is mode of f of x minus L plus mode of g of x minus m. And to write down this is less than epsilon, I just adjust here epsilon by 2, here is epsilon by 2. Because epsilon is arbitrary, which is given to us. So that's why this is epsilon by 2 plus epsilon by 2 equal to epsilon when d1 of x minus a is less than delta. So since this is there, this two condition is satisfied. And so from this statement 1 and statement 2, we can say that this is true. This is because of statement 1 and 2. And which completes that, prove that a limit of f plus g of x is equal to L plus M. So therefore, limit of f of x plus g of x is equal to L plus M as x tends to a. Now the second I already told you to do it your as a homework. It's similar kind of things you will have. Now to prove the third one, that fx limit of fx into gx is equal to L into M. So what we can have, we'll start with this quantity. So that I'm doing some rough work here, that if I want to prove that quantity, then I have to prove that fx into gx minus L into M is, I want that this has to be less than epsilon. So that's why I have to add and subtract some terms here, and we can add and subtract that L into gx minus Ln into M. Now from this two quantity, we'll see this gx is common out, and by triangle inequality we can write down this is less than or equal to, plus from this two we can have this L is common out, so it is mod L, mod of g of x minus M. So ultimate goal is to prove that this is less than epsilon, this quantity. Since f is has a limit L, so this will less than some quantity. Here is also no problem because that we can adjust with this L. The problem is with this g of x. So I want to prove that this g is the bounded function. If I can prove that this is less than epsilon, I have to prove that this is a bounded function into some neighborhood of a, small a. So that we will going to prove first, that this g of x is the bounded function inside the neighborhood of a. So what is given is limit of g of x is M as x tends to a. So by definition, what we can say is, for given epsilon greater than 0, and for timing I'm just choosing this epsilon is equal to 1, which is greater than 0, such that, let's say, delta 1 and delta 2 we already used earlier, so that's why I'm just taking delta 3 greater than 0, such that distance whenever this x minus a is less than delta 3 implies this fx minus M is less than 1. So what we can say is, this mod of g of x minus M is less than 1 whenever this x, it is in this neighborhood delta 3 of a. So in this neighborhood, this is the situation is there. Now I will start with, for any x in this neighborhood, S3 of delta a, delta 3 of a. Mod of g of x, we can add and subtract M here, and by triangle inequality we can write down this is the quantity we have this. So this is less than 1 plus mod M for every x is in this. So what we have proved is g of x is bounded by 1 plus mod M whenever your x is in this neighborhood. So I can state that, therefore g is bounded in S delta 3 of it. So in this neighborhood, the g is bound. So ultimately what we get is mode of g of x is less than 1 plus m for every x in this neighborhood. So we can write this as a statement that therefore mode of g of x is less than 1 plus mode m for every x belongs to S delta 3 of x. This I will call it the statement 1. Now, to take this one, that is mode of fx minus L, this is already less than 1 plus m, mode m. So if I want this is less than epsilon by 2, then it has to be epsilon upon 2 plus, sorry, 2 into 1 plus mode m is there. So this 1 plus mode m is cancelled out. So this will left with epsilon by 2. So that's why now for this limit x tends to fx is equal to L for given epsilon greater than 0, there exists, I will say delta 1 and delta 2 greater than 0 because we'll write both this statement together. We have fx minus L is less than epsilon upon 2 1 plus mode m as I have discussed. For every x is in this, or I can say for every x is satisfying 0 less than d of x minus a less than delta 1. Here is also there will be a deleted neighborhood. So it is minus a, it has to be there. So we have this. And mode of g of x minus m is less than. Now what we required in this previous case, I want that this quantity is also less than epsilon by 2. So that's why this quantity should be less than epsilon upon 2 into 1 plus modal. Why I have taken this 1 plus modal? Because we don't know whether this L is 0 or non-zero. If it is 0, then I cannot define 1 epsilon upon 2 into mod L. If L is 0, then we cannot define. So that's why I'm adding 1 there. So now this mod L upon 1 plus mod L is always less than 1. So there is no problem by adding 1 here. Because ultimately I want that this has to be less than epsilon by 2. So that's why this I'm taking as epsilon upon 2 into 1 plus mod L. Whenever this x, it is in satisfying this condition less than delta t. Now we'll choose our delta, which is the minimum of delta 1, delta 2, and delta 3, which come from this delta 1 definition here. This is delta 2 and delta 3. So whenever this for any 0 less than del d of x comma a less than delta, by consider, so for any, you can write down x which satisfying this, consider this mode of fx into gx minus L into m. Add and subtract as I told you to adjust L into gx plus L into gx minus Lm. So this is less than or equal to by triangle inequality. From this two we can common out mod gx, that is fx minus L plus mod L gx minus M. So using this 1, 2 and 3, we can say that this is less than 1 plus mod M. This is epsilon by 2, 1 plus mod M plus mod L into epsilon by 2, 1 plus mod L. So in the previously we have taken that here from 3. This is because of 1, 2 and 3. Whenever your x is satisfying that condition, that is in that neighborhood of delta. So that is equal to epsilon by 2 plus epsilon by 2, which is equal to epsilon. So hence this limit of f of x into g of x is equal to L into M as x tends to A. So that is prove that a product of limit is the limit of product. Now the next quantity or next result that we have, it is the about the product, sorry, division. That is a limit of division of a two function is a division of a limit. So ultimately I want to prove that limit of fx upon gx is equal to L by M as x tends to A. So if I use the product rule, which we already just now proved that, then it is sufficient to prove that the result is true for 1 upon g of x. Because if I prove the limit is true for 1 upon g of x, then I can apply the previous result for product rule and will get this result. So we shall show first this one. So we can write down we shall show that a limit of 1 upon g of x is equal to 1 upon m as x tends to a. So g is non-zero, g of x is non-zero is given. Okay. So we have given that limit of g of x is equal to m as x tends to a. And I have to prove this is the things. Now, if to prove this one, we'll just see what is this quantity. I have to prove that this minus this is less than epsilon. And if you take the LCM, you will have g of x into, sorry, minus m upon g of x into m is there. So this is less than, I can say this is mode of g of x 1 upon mode of m into this quantity is less than epsilon because this is given. So that's why it is less than epsilon. But this epsilon I have to adjust to that values, this values. But we don't know whether what is this 1 upon g of x is there, whether it is a bounded or unbounded. If I can able to prove that this is bounded, then we are done. So we'll show that this is bounded into the neighborhood of A. Okay, so for that, this is given. So for given epsilon, or let epsilon to be greater than 0 to be given. And this m is non-zero, it is also given. So there exists some delta 1, I can say greater than 0, such that mode of g of x minus m is less than epsilon. Let us take this epsilon as mode of m by 2, which is greater than 0. So hence, what we have is mode of g of x minus m is less than mode m by 2 when whenever, here is also I should write, when 0 less than delta d of x comma a is less than delta 1. So when this is the situation there. Now if I expand this modulus, then I can rewrite that is this quantity, and we'll use the one equality inequality for the real numbers, that is this mode of a minus mode of b is less than or equal to mode of a minus b. If I use this inequality, then we can write down mode of g of x minus mode of m is less than or equal to mode of g of x minus m less than mode of m by 2 when whenever this d1 of x comma a is less than delta 1. So therefore this will gives you minus mode m by 2 less than mode x minus mode m is less than m by 2. If I add m both side or this side, then it will be mode m plus minus m by 2. So that is mode m by 2 less than mode x less than mode m by 2 plus mode m, which is 3 mode m by 2 when your x is satisfying this condition. Now since I want to prove that 1 upon mode g of x, see if I want to prove that mode g of x is bounded, then I can use this quantity. But here I want to prove that 1 upon mode m, so I am using this one. So therefore this says that mode of g of x, 1 upon mode of g of x is less than 2 by mode m, and which will define because m is non-zero when x is satisfying this condition. We call it this statement as 1. So now we have deal with this 1 upon g of x. Now we have to deal with mode of g of x minus m. So for that, for given epsilon greater than 0, we already have. So now further, there exists delta 2 greater than 0 such that mode of g of x minus m is less than epsilon into mode m square by 2, because here we have this is mode of g of x minus, so this is less than 2 by m, and that 2 is we need to adjust, so this will be less than 2 by m, 2 by mode m, so it is 2 upon m mode m square is there. So I want to adjust, this is less than epsilon, so this has to be epsilon m square upon 2. So that's we have taken here epsilon m square upon 2. So now choose whenever this 0 less than delta 1 less than delta 2. Now we have to choose this delta will be minimum of delta 1 and delta 2. Now we'll start with or considering this 1 upon g of x minus 1 upon mode m. If you take the LCM, this is, we can write g of x minus m upon this g of x into m. By the property of modulus, we can write down this is equal to mode of g of x minus m upon mode g of x mode m, which I can write down less than 2 upon mode m square into mode of this one, it is epsilon mod m square upon 2. This is because of result 1 and 2. Whenever 0 less than d of x minus a less than delta. So whenever this quantity is there, this is will be there, and that is equal to epsilon. So hence we can write down that therefore limit of x tends to a 1 upon g of x is 1 upon m whenever g of x is limit of g of x is m as x tends to a. So now we'll start with limit of fx upon gx is equal to limit of fx into 1 upon g of x as x tends to a. And using the product rule, we can write down limit of x tends to a fx into limit of 1 upon g of x as x tends to a. This limit is L, and this we already proved that it is 1 upon m. So this is L by m. So that's proved that division of a limit is a limit of a division. With this, we able to give you a definition of continuous function. On a metric space. So let x comma d1 and x2 comma d2 be a metric space, and a is belongs to x. Let f be a function from x to y, then f is said to be continuous at the point a in x if given epsilon greater than 0, there exists a delta greater than 0 such that d1 x minus a is less than delta implies d2 x minus f of x minus f of a is less than epsilon, or into the other way, or that is as a theorem we can, or in the terms of neighborhood definition we can say that there exists a delta greater than 0 such that x is belongs to this neighborhood delta of a, which implies f of x is in this neighborhood epsilon f of a, and it is denoted by limit of f of x is equal to f of a as x tends to a. Then we can say that f is continuous at the point a. Now we have one important result based on equivalent condition or equivalent statement on this continuous function that we will discuss in the next lecture. So till then we can stop here. can ask a question if you have.